In this video, we will discuss the composition of functions and the difference quotient. So we're going to start with composition. And in college algebra, you learned how to compose functions together. And we're going to do an example of that just to refresh our memory. When we compose functions together, we're given two functions. In this case, f of x is the square root of 3x minus 1. And g of x is x minus 5. So let's make sure that we understand the notation, f composed with g of x. You can also write this as f with a little circle, f of g of x, if the extra parentheses there confuse you. So let's take a look at what the domain of the function f is. So the domain of f would mean that 3x minus 1 would have to be greater than or equal to 0, because we know we can't take the square root of a negative. So in this case, x has to be greater than or equal to 1/3. For g, the domain of g, we don't have any restrictions. It's just a polynomial. So the domain here is all real numbers. And then how do we compose them together? Well, when I look at a composition like this, or even like this, f is what I call my outer function, and g of x is my inner function, and my outer function is my template. So in this case, f composed with g of x, I use f as my template, which is the square root of 3 times something minus 1, and the g of x is my inside function, which is x minus 5. Now we could plug anything we want into the g function, but in the end we have to make sure this is going to give me 3x minus 16. We have to make sure that 3x minus 16 is greater than or equal to 0. So for the composition, the domain of the composition is x has to be greater than or equal to 16/3. All right, in calculus, we oftentimes decompose functions. In other words, we want to know what were the functions that it came from. So we call what we use it for is something called the chain rule, and we have to be able to identify, looking at something like h of x equals 3x minus 7 to the 4th, we have to be able to identify the functions that came from. So if we interpret h of x as a composition in this case, I might think of my outer function as f of x equals x to the 4th, that's this outer function here, and the inner function here being 3x minus 7. So if I wrote f of g of x, I would get that 3x minus 7 to the 4th. Let's take a look at a couple of other functions and try to decompose them. So when I decompose something as f of x times g of x, I want to identify the f and g functions, the outside function and the inside function. So in this case, our outside function would be sine of x. So I'm going to call that my f of x. And my inner function, 3x minus 6, would be my inner function, or g of x. Very often in calculus, we don't just compose or decompose two functions. We have 3 or 4 or 5 functions that we're talking about. So I hope you can see here we have a tangent, we have a square, and we have a 5x minus 3. And we want to identify h of x as f of g of k of x. So let me first rewrite this. This one can be a little confusing. But this is really the tangent of 5x minus 3 squared. When we write tangent squared, we're saying the tangent is the thing that's squared, not the argument. So I can see here that my outermost function is my square, and I'm going to say f of x equals x squared. My next inner function would be tan of x, so I'm going to call g of x equal tan of x. And the third one, k of x, is 5x minus 3. So if we were to take f of g of k of x, f would be our template, and our outermost function is a square, so we're going to say squared. And then g of x is tangent of something, so we're going to plug g in here, tangent of something, and then the something is that k of x, which is 5x minus 3. Oops. Also in this section is the difference quotient. In this class, we study lines, or linear functions, and we are able to find the slope of a line if we're given two ordered pairs, or possibly a graph, or an equation in the form y equals mx plus b. But in calculus, we might want to find the slope of a curve at a particular point, in which case we would only have one ordered pair, so we couldn't use our slope formula. So to do this, we start with the slope of a secant line, and a secant line is a line that touches the graph at 2 points. So for this example here, our 2 points would be this point here, which is x comma f of x, and this point up here, which would be x plus h, keeping in mind this is the distance h, and then our function value at x plus h. As we move the point x plus h closer and closer to the point x, we notice that the secant line actually turns into the tangent line, and that happens as h gets close to 0. So let's take a look at what that looks like. So what does that look like? Well, as we move that point closer and closer, so our point that was here at x plus h, we'll put that in here. As h gets closer to 0, that line actually becomes this line, so close together that we just touch the curve in one point, and that's called a tangent line. So if I start with my x plus h and f of x plus h, and of course just my x, f of x, the slope of those 2 points is y2 minus y1, so f of x plus h minus f of x, divided by x plus h minus x, which simplifies into this expression here, which is the slope of the secant line, so two ordered pairs. And then in calculus, we take one step further, which we're not going to do in this class, but I just want to show you. We're going to take the limit as h approaches 0 of this expression, and that's going to give us the slope of the tangent line. So this would be the slope of the tangent line. But we're going to focus now on finding the slope of the secant line using the difference quotient. So I've got a couple of examples here. Let's start with finding the difference quotient of the function 2x squared minus 3x plus 5. So just for reference here, I'm going to write down the difference quotient. I'll call it the DQ. F of x plus h minus f of x all divided by h. So to do this, I want to find f of x plus h first. So just like anything, f of 3 or f of 4, we just plug x plus h here in for the x. So we're going to have 2 times x plus h quantity squared minus 3 times x plus h plus 5. Simplifying, I have to FOIL, don't forget. So we'll get x squared plus 2xh plus h squared minus 3x minus 3h plus 5. And simplifying a little bit further, we get 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 5. So we just found this part of the difference quotient. Now, let's put it all together. F of x plus h would be this long thing, 2x squared 4xh plus 2h squared minus 3x minus 3h plus 5 minus our f of x, which was given to us, 2x squared minus 3x plus 5, all divided by h. Now what you should notice is that once I distribute this negative sign through, 2x squared minus 2x squared adds to 0, minus 3x plus 3x adds to 0, and 5 minus 5 adds to 0. So we end up with 4xh plus 2h squared minus 3h all over h. My next step would be to factor an h out of the top because I notice it's in each term. And then I can cancel. So the difference quotient for this function is 4x plus 2h minus 3. So just a quick note, let me write it up here. Make sure you're finding f of x plus h, which means plug that x plus h in, not f of x plus h. So you don't want to just take this and add an h to it. That would be wrong. You want to actually plug the x plus h into the function. So try the next one on your own. So pause your video and I will write down the solution and then we'll do the last one together. So hopefully you found your f of x plus h first and got 3x plus 3h plus 5. Plugging that into the difference quotient, adding like terms, we end with 3h over h. The h's then cancel and we get 3. Well, that should make sense because this is a line and the slope of that line is 3. So let's take a look at the last example. This one is a little bit more complicated, so we'll do it together, but you will see things like this in calculus. Let's start by finding f of x plus h. That means plug x plus h into f of x for x. Actually, this is g of x plus h. I didn't notice that. Okay, so this can't really be simplified. So when I put it in my difference quotient, we're just going to have g of x plus h minus g of x all over h. So that's going to give us the square root of x plus h plus 4 minus the square root of x plus 4 all over h. So notice when I distribute that, it becomes positive 5 and minus 5 plus 5 add to 0. Now, technically this would be good, but what we want to do is rationalize the numerator. And we do that by multiplying by the conjugate of the numerator. So we're going to multiply by x plus h plus 4 plus x plus 4 on the top and also on the bottom. What happens when we actually multiply this out? Well, here when you multiply a radical by itself, you get x plus h plus 4. On the outsides, you'll get plus the square root of x plus 4 times the square root of x plus h plus 4. When you do the insides, you'll get minus those same two things. And then when you multiply the last, you'll get actually minus, when you do these two, minus x plus 4 all over h times x plus h plus 4 square root plus the square root of x plus 4. So I know that this now showed up in the bottom, but you should notice that because I'm adding and subtracting the same thing, those go away. So if I simplify just a little bit further, I end up with x plus h plus 4 minus x minus 4 over h times the square root of x plus h plus 4 plus the square root of x plus 4. The x's are going to add to 0, the 4's are going to add to 0. So these are all going to add to 0. And we will have h over h, the square root plus the square root, and those h's will cancel, and I'll just get 1 over the square root of x plus h plus 4 plus x square root of x plus 4. So this is a concept that you definitely will use in Calculus 1, rationalizing the numerator, and we tend to see it show up when we're finding a difference quotient. Thank you.